Hello everyone, welcome to G-Centric. So in this lecture we are going to start with the other three types of filters. Okay, so we have seen already low pass filter and high pass filter in the previous lecture. Now in this band pass filter, okay, it means that it is going to allow certain band width. Okay, between that band width or between those two range of frequencies we are going to get a band, something like that. Okay, so now how we are going to use this one? First we will go with the using Laplace transform and getting the transfer function. Okay, so let us convert everything in L domain. Okay, so this will be equal to 1 over Cs, this is Ls, and that will be R all the time. Okay, this is the Laplace domain for the circuit. Now I will take out the transfer function. Basically I can apply voltage division rule. So if I want across R, okay, so the output is V naught of S, the voltage division rule where I want to apply, and this is 1 by Cs plus Ls plus R times Vi of S. Okay, so now the transfer function V naught of S divided by V of S, H of S is equal to, so this Cs multiply, take the LCM, and Cs will go over the top, okay, and divided by, this is nothing but then we have got here 1 plus LCS square plus RCS. Okay, correct. So now here this is in S domain, right? S equal to J omega. Substitute this one, or else you can take RC also as common. Okay, then you can, this will be RC over here, 1 by RC plus, so CC will get cancelled, it will be L by R S square plus S. Okay, so this RC and the numerator RC will get cancelled. Substitute J omega over here. Okay, J omega, and this will be minus, and here it will be J omega. Okay, so when you take the magnitude of this one, you will get omega root of, okay, so omega square plus 1 by RC whole square plus L by R whole square. Okay, here is there's one more omega. Okay, omega, right? So this is the thing you will get when you substitute for, or when you take out the transfer function. But now you can observe that still the magnitude of the transfer function is dependent on, okay, H of J omega magnitude dependent on frequency. Okay, keep this thing in your mind. Okay, this is an important point to solve this circuit. Okay, now we will go with our second method. Okay, from the second method. Okay, this is half solved, so you can continue it later on. Now during omega equal to 0, what will be XL? It is omega L, so it is 0 ohms. It means it is short circuit path. Okay, XC is infinite ohm, it is open circuit. Okay, similarly when omega is infinite, XL will be equal to infinite ohm, which means it's open circuit, and our XC will be 0 ohms, which means it is short circuit. Okay, till now it is clear. Now we will put the apply this thing in for this circuit. So first we will see for omega equal to 0. So when omega equal to 0, XL is 0 ohms. That means it's a short circuit and capacitor will be open. Okay, let us draw the circuit over here. So capacitor is open and this is short circuit. Okay, R will be as it is, and this is V naught. Okay, here is Vi. So now what do you observe? There is no drop over here, current is 0, over here also current is 0, so there won't be any drop across resistor as well. So V naught will be equal to 0 volts. Okay, so there will be no voltage across the resistor, right? So if it is 0 volt, directly this V naught will appear over R. Okay, so it is 0 volts. Next we will see for omega equal to infinite thing. Okay, when it is infinite, XL will be short, open circuit and capacitor is short circuit. right? So this is short circuit for capacitor, inductor, and we have the resistor. So this is V0, R and Vi, right? This is C and L. So again, if you see, this is again open circuit and here also open circuit. So again V0 will be equal to 0 volts. Now what does this indicate? It doesn't mean that there is no band in it, okay? Moving from 0 to infinite, when omega is moving from 0 to infinite, it means that there is some 0 volt appearing for here also, over here also. That means in between some frequency, which we will call it as cutoff frequency, let us say it's a cutoff frequency, we will get a band. Okay, after that initially it will be 0 and in final value also it will be 0. Okay, so our graph versus frequency with magnitude will be somewhat like this. Okay, so let us take this as omega 1, omega 2, okay, and this is some cutoff frequency. So this is for ideal graph, but if you take the practical graph, so somewhere it's going to start over here, you will get like this and it will move on like this. Okay, so this is practical. It doesn't mean that from 0 volt to 0 volt, that is, it's nothing going to be appearing, okay? It's not like that. Since still this transfer function is dependent on frequency, that's why I said this point is important. It will have somewhere, there is a band in between, okay, that is going to be available in between the high frequency, low frequency and high frequency. So now how to identify in a circuit, okay? So whenever this condition appears, right? So when omega is equal to, let us say, cutoff frequency, it appears when XL will be equal to XC. Okay, so when this condition is there, it is resonance. Okay, whether parallel or series, you can tell this circuit as band pass filter. Okay, some amount of band will allow to pass. Okay, some amount of or few range of frequencies this band is going to allow. So this is the band pass filter. Okay, and also there is one more note point over here. Okay, when high pass filter and low pass filter are connected in cascade, they are in cascade now, right? Okay, and also it should satisfy the condition that higher frequency should be less than lower band frequency. Then only we can say that it is a band pass filter. Okay, so this is one more condition that you can easily identify that it is a band pass filter. So now in the next circuit we will see band rejection or band elimination circuit. Okay, so coming to this band rejection filter, or you can call it as elimination filter as well. Okay, so what does it do? It will eliminate some range of frequencies and it will allow only some range of frequencies to pass through it. Okay, so now again we will convert this all into Laplace. Okay, this is Ls and this is 1 by Cs and this is V0 of S. So our transfer function will be, okay, V0 of S divided by Vi of S equal to, okay, so now this is the voltage across here. So these are in series, right? So Ls into 1 by Cs divided by R, okay, together. So this is not, this is plus R plus 1 by Cs plus 1 by Ls. Okay, when you solve it, still you will get that it is dependent on frequency. Okay, substitute S is equal to j omega, you will get still that it is, you will not get a constant but you will get some omega term in the transfer function equation. Okay, this is homework for you, you can do it. Next, coming to our second method. Okay, so substitute. Now here there is a twist. See here, omega equal to 0 or omega equal to infinity. Any one of the element will be either open circuit and either or short circuit, right? So it means that this path will be open always. Okay, so if I have to redraw this circuit, even for omega equal to 0, Okay, let us take this as 0 ohms first, right? So inductor will behave like a short circuit and capacitor will behave like a open circuit. Okay, so this is V0 and here is Vi. So now here if you see, there is no drop over here. Here also there is no drop. So Vi is equal to V0. Okay, this is for omega equal to 0. Next, omega equal to infinite, same circuit we will get. Only thing is, here inductor will be open but capacitor will be short circuit. Okay, but still the path remains open. So now again we are getting, there is no drop over here. V0 will be equal to Vi. Okay, what does this mean? For high frequency as well as for lower frequency, we are getting the value of output. Okay, so it means that if you want to draw a graph for this one, okay, so first let us take it as 0. It is allowing some band over here, then it's getting to 0. After some time again it is allowing some band to pass, right? So it is rejecting here, it is rejecting here and getting some value. Okay, so this is the type of filter. When both the sides you are going to get some output, it is the band rejection filter. Okay, again here also, if you have low pass filter, okay, and high pass filter connected in parallel, okay, so when connected in parallel, higher range of frequency should be greater than the lower range of frequency. Then you will call it as band rejection filter. Okay, so this is for the band rejection filter. Now we will move on to all pass filter. Okay, so basically if you are getting some output, you can assume that here there is something called as like this line. It's a straight line. It means this is the graph for resistor. Okay, in resonance also we have seen this as resistor graph, and somewhere over here we have taken XL and XC. Where we have taken XL will be equal to XC, that we had called it as resonant frequency, right? So this graph is basically for R, right? But this shows that it is irrespective of the frequency terms, because we are going, x-axis is about the frequency and this is about the magnitude. Irrespective of the frequency values, this is remaining constant. Okay, the value of magnitude is constant. That is for all band pass. Okay, we will see this now. All band pass filter. Okay, but here this is for ideal graph, right? Practically this graph will be somewhat like this, and again it will go like this and like this. Okay, this is about the band rejection filter. Okay, now we will see about the all band pass filter. Okay, so coming to this section, we have got all pass filter. Okay, you can take any type of circuit, but this is one of the complex circuit that I have taken to make you understand easily. Okay, so now instead of going into our old method, we will derive this by transfer function, taking the Laplace transform. Okay, so that we can prove that when resistor is independent of frequency, then we will get all pass filter. It does not depend on the frequency. Okay, so to begin with, H of S is nothing but V0 of S divided by Vi of S. So now we know this is Vi, it will occur over here, okay, across this branch. Same Vi will be over here as well. Okay, convert this to Laplace domain, Vi of S. Okay, so now first I will take this as VR and here is VC. Cool. Next, I will apply the KVL in this branch. Okay, so basically we are doing only to get the relationship between these two. Okay, we do not want all these terms in our equation. So now if you apply KVL, you will get plus VR minus V0 minus VC equal to 0. Okay, if I take V0 over there, VR minus VC. Now VR, I can directly tell that since it has got same value, it is Vi by 2. Okay, Vi by 2. Now to find this VC value, okay, I can apply voltage division rule. Okay, Vi of S will be equal to, I want across VC. So VC of S is 1 by Cs divided by 1 by Cs plus R. Okay, so CS gets cancelled, you will be left with 1 plus RCS. Okay, substitute that over here. 1 by 1 plus RCS times VI of S. Okay, here multiplied with VI of S. It's a voltage division rule. Okay, now this equation I will write it over here. Okay, VIS is common. I will take it out. V0 of S by VI of S 1 by 2 minus 1 upon 1 plus RCS. So now this constant term, I will take this one out. 1 by 2 minus, okay, so you will get 1 upon RC, 1 by RC plus S. Okay, so this RC I can take it up. Okay, 1 over RC divided by, so this is S plus 1 by RC. Okay, just I'll verify if it's correct. Okay, so now over here I can take the LCM. Okay, so here also I will get S plus 1 by RC minus 2 by RC divided by S plus, this is twice, S plus 1 by RC. Okay, so this, if I take it out, simplify it, S minus 1 by RC divided by 2 times S plus 1 by RC. Okay, correct. Now I can just separate it over here. Okay, V0 of S by VI of S equal to, okay, this magnitude, how will I take the magnitude? Put j omega over here, you will get S is equal to j omega. Substitute this one in the equation. So let the 2 be outside. Okay, so if I take the magnitude, since it's up also there is a S term, I can take the magnitude over here plus 1 by RC whole square. Okay, plus or minus term doesn't matter now. Omega square plus 1 by RC square. Okay, so now I can cancel out this term. I am left with 1 by 2. Okay, so if you observe over here, there is no omega terms. Okay, it is independent of frequency. So you can conclude that when it is independent of frequency, it is the all pass filter. Okay, I hope you have understood this one. So we will see some of the questions asked in the electronics branch based on this concept. Okay, we will see question based on the passive filters. So in both the circuits, they are asking what does this type of circuit represent, what type of filter it is. So coming to this question number 253. Okay, so we will always convert this to Laplace domain first. Okay, this is yes, R is as it is. This will be equal to 1 by L1S equal to 1, sorry, this is L1S and this is C1S and this is L2S and this is 1 by C2S and this is V0 of S. Okay, so now if you see this branch, okay, if you see a branch over here, both these elements, either for omega equal to 0 or omega equal to infinite, one of the element will be open. Okay, so hence we can conclude that this branch will be open circuit all the time. Coming to this combination, it's in parallel. Okay, one of the branch will always be short circuit. So our diagram will look like, so this is Vs, this is Rs, and here definitely we will be having a short circuit path. Okay, and here we do not have V0 of S. This will be always open. Here there is no drop, but they have got a drop or output voltage for this one. V0 of S is equal to Vi of S. Okay, so this is Rs circuit, right? Sorry, this branch is missed. Okay, this branch RL, I will put it over here. Okay, so this is gone. Okay, so this is what the circuit looks. So if I want V0 of S upon Vi of S, okay, so I will take the RL, Rs plus, okay, RL times Vi of S. voltage division rule. This is same for omega equal to 0 as well as omega equal to infinite, right? Because the circuit won't change. This will always be open circuit and this will always be short circuit. You can try it by yourself as well. So for both the values, we are getting the same value for both the frequencies, higher range as well as for lower range. But if you see here, this is an R circuit. Please do not assume that it is independent of frequency. Since in this options we do not have all band pass filter, we cannot conclude directly that it is an example for the all band pass filter. Okay, so now this cannot, since we are getting output for both the frequencies, it cannot be low pass or high pass. For band pass filter, we have to have the outputs as 0. That is also not available. So it is band rejection filter. Okay. Solve this using the transfer function fully, then conclude that whether it is all band pass filter or no. Okay. Coming over this circuit. Now, in this circuit also, first we have to analyze for 0. Okay. Since only capacitor is involved, we will analyze it only for the capacitor. So Xc will be equal to 1 by omega c. When it is 0, it is infinite. It means open circuit. Okay. So when it is infinite, Xc will be equal to 0 and it is short circuit. So for first we will analyze for omega equal to 0. It is the open circuit. Okay. Remove this one and remove this one. So what you will get? Here there is no voltage drop. There is no current flowing over here also. Okay. So V0 will be equal to 0 volts. Okay. Same for the infinity. It is a short circuit path. Okay. So when it is again short circuit, this will be 0 volt. This will be also 0 volt. So voltage across resistor will be 0 volt. Right. So in this also we had 4 options. It cannot be low pass, high pass or band rejection. It is band pass filter. Okay. Next, coming to question number 255. It was asked in GATE 2007 in electronics branch. These questions were also asked in electronics 2000 branch. Okay. In EC branch in 2000. So this question says that, question number 255, 2 series resonant filters are shown. Okay, filter 1 and filter 2. Let the 3 dB bandwidth of filter 1 be B1. Okay, they have said that bandwidth of this filter is B1 and that of filter 2 is B2. Okay, we have to find B1 upon B2, the value of that one. So we have seen in the resonance chapter that the relation between bandwidth, quality factor and cutoff frequency. Right. So here the bandwidth is, when it is only RLC circuit, okay, see here RLC circuit, the bandwidth for this one is R by L. Okay, this is R by L. So for this also it is R by L and here also it is R by L. So P1 is equal to R by L1. Okay, and here for B2 it is R by L2. But we know that L2 is L1 by 4. This is 4 times of C1 and this is L1 by 4. Okay, if it's not visible, this is L1 by 4. Okay, so instead of L2, I'll put L1 by 4. Okay, so bandwidth they have asked B1 upon B2. So R by L1 by 4. Okay, these two gets cancelled. So we are left with 1 by 4. So this is the answer for this question. Okay, you need to know what is the bandwidth for the filter. Okay, so this completes our passive filters chapter. In the next lecture, we will move with the graph theory, and that's one more chapter is there, that is locus diagram, and after that we are done with the network theory. Thank you.